I think this is a good problem. There's a lot to learn here. Which of the following functions are meromorphic on the whole plane? So it didn't say what's the word? The extended complex plane, right? This is not C union infinity. This is just the complex plane. So with that in mind, this is meromorphic. In fact, this would still be meromorphic on the extended complex plane, right? Remember, the rational functions are the only meromorphic functions on the extended complex plane. This is not meromorphic because it's got a singularity which is not isolated. Meromorphic functions have to have only isolated singularities. This one has singularities at the third roots of -1. So it's got 3 singularities. They're all poles. It's meromorphic. Here the origin is an essential singularity. Therefore, it's not meromorphic. Remember, meromorphic function has isolated singularities, each of which is a pole. So if you've got an essential singularity, we're not looking at a meromorphic function. This one here, tangent z, has a simple pole at wherever the cosine is 0. It's simple because sine is non-zero wherever the denominator is 0, you know. And so that is meromorphic because these are isolated. However, if you were to look at the extended complex plane, it would no longer be the case because there's infinitely many of them in a neighborhood of infinity. So these singularities bunch up around infinity is the way we look at it. This one, it's got a double pole at 3. That's the only singularity, so it's meromorphic. All right. Yeah. All right, what else was I supposed to show you guys? Something else. What was it? Oh, mission 6. Yeah, mission 6. Let's see here. So I've definitely asked this question as a test question many a time. Like, this calculation is important to me, that you understand it. You know, how to find the Laurent series for, not this specifically, but generally speaking, how to find the Laurent series of a rational function where we use the geometric series in order to set up the Laurent series. You know? Oh, there was something in here I wanted to show you guys. There's something nefarious. There's something just stupid thing. Like, I was minding my own business, trying to, like yesterday I was like, all right, I got some time. I'm going to finish these solutions. Everything's going to go great. I worked problem 77. I was like, yeah, done. You know, problem 77 was just like, yes, easy. You know, it was just, you know, like taking candy from a baby and the baby's asleep. Because if you know anything about babies, taking candy from when they're awake is actually quite difficult. But then this, I was starting to feel ill at ease here. I'm like, okay, well, all right, not too bad. But it's an essential singularity, right? Because it just keeps getting worse past here. But fine, you know, fine. This thing is evil. My solution here is not, nope. I mean, I completely ignored the, modulus is between 0 and 2 pi, which matters, of course, because this thing has singularities at 2 pi I multiples of the integers, because e to the 2 pi I is 1, e to the 4 pi I is 1, e to the 6 pi I is 1, e to the minus 2 pi I is 1, right? That's why this is here, because past that you've got other singularities and you start getting different Laurent expansions on those other annuli. There's countably many different Laurent expansions for this as you go out from the origin, each on an annulus that goes from, the last 2 pi multiple, whatever. So I was completely ignoring this data as I was doing this expansion. Like, I'm expanding in this radius of this power series, but that's not legitimate because I don't actually know that's less than 1, which is why this is wrong. I don't know if this is correct anywhere. All right. So I'm like, all right, well, great. How do you do this stupid thing? And I haven't researched it yet, so I don't really know the ultimate answer, but I found myself needing to use chapter 6 stuff to do this problem. So what I did was, to find the first term, I calculated the residue using the rule, what? I guess basically rule 0, paired with a little power series calculation. Notice that e to the z minus 1 is the sum of all of the higher order terms in the exponential, and I factored out a z. That shows you that it's simple pole, right? Because you got a 1 over z times something that's non-zero. Remember? That's our like I was telling you guys to start class. All right, so great. That's my residue. How do I get this thing here? Well, I was like, I guess I need to do this integral then, because that will calculate. That's one way I can get it anyway. It's equal to this integral. But probably I'm just kind of hiding the fact that I'm really just using the residue. I'm using the residue of, anyway, so that means I have to calculate the residue of this thing, which is not the same thing I did last time, right? Because now it's got a z squared rather than a z. So I got to use rule 2. It's a double pole, So I do that, and there that is. So I used rule 2 to get that. And then to get the next coefficient, I had to use rule for a triple pole. To get my pause on the A1, I did that. And then this is the answer in the back of the book, right?
Can't you do long division? That's what you told me to do in office hours.
Did long division work?
Long division works.
Dang it! Man. See, this is the cost of me doing homework when I'm sleepy, is I find harder ways to do things.
Wow.
Rats. So I'm told long division is a good solution. Well, that's lovely. Why didn't I tell myself that?
Really?
Rats. Well, anyway.
Your grader was on top.
I identify a lot with, there's like a mathematician named Sylvester, and I like that guy. I kind of feel a lot like him. I've read stories about him. He'd be convinced this is wrong. This can be disproved, and then his students would be like, but professor, you proved that's true 3 weeks ago. I feel a certain camaraderie with Sylvester. But anyway, so great. Well, I guess I don't need to do that. That's good. That's good. Wonderful. I think, have I suffered enough today yet? Can I stop? Show you cute pictures of Benjamin.
Can we also look at the Roche's question?
On this one? Yeah, we can do that. So these are actually, I think, good questions. Like, if f and g have a pole, does f plus g have a pole? Well, no. You can just take one as the negative of the other. They both have poles, but their sum is 0, right? On the other hand, if you've got one as a singularity, there's nothing you can do to get rid of the infinitely many terms which are non-zero and the negative powers, right? So yeah, you got all these terms. They add together where they're non-zero, but down here there's no way to cancel them. So yeah, it's still essential. I like this. I thought these problems were kind of cool. Let me skip ahead to the Roche. Oh, this is what I was going to talk about. The behavior at infinity. There's 2 different ways to go here. The one is with the reciprocal function theorem. The other is just to recognize your foe. So if I have a polynomial, an unending polynomial that's defined on the complex plane, that makes this an essential singularity at infinity. On the other hand, if I have only a few polynomial terms and then all just reciprocal terms, that would make it a pole at infinity. All right, so it's kind of backwards. Like this one here, I got 1 plus reciprocal terms. So this is actually analytic at infinity because it's got no polynomial piece. This one here, again, is analytic at infinity. This one, since it's got a quadratic term, that makes it a pole of order 2 at infinity. Now, we could run all this stuff through that reciprocal function theorem, the definition, right? It's not even a theorem, it's really the definition of what we mean by a pole at infinity, right? We can always go back and do g of w as f of 1 over w, and then our theorem was, our definition was that f has a whatever at infinity if g has a whatever at 0. And that whatever could be a 0, it could be a pole, it could be a central singularity, all of the above, you know? So like I did that here, so g of w is tangent of w. That's analytic at w equal to 0, which means that f of z is analytic at infinity. I just found that more convenient for this problem, but the rest of them I kind of looked at in terms of the, all right, so you said the Rochets. Which one was that?
The last, second to last.
Second to last. I like these. These are cool. That's actually a lot of fun. Don't you think? Oh. Oh, well, I thought it was fun. Let's see here. Yeah, it was cool. You skipped it, huh?
That wasn't bad. It just took me a real long time. Yeah, the algebra. I was just like, well, scrap paper.
That one's kind of beastly, isn't it?
But it's nice that you finally get it.
Are we talking about this one, Shane?
That's correct. Yeah.
All right. So the idea here is to find the number of zeros within 2, and then also find the number of zeros within a half, and then you just subtract to get the number of zeros between a half and 2. So if we're looking at a half, we can use that as our nice function, and we can use the rest of it as the perturbation. And then, so if we got modulus z minus 1 to the half, then modulus of f of z is actually 5 there, whereas h of z is at most 4.5, which is of course less than 5. So yay! Roche's theorem says that there is 1 0 within the half radius circle centered at 1. But before I do any of that, the first move that you must do, and this is like general advice, is if you've got data centered at 1, you must take the formula and recenter it at 1. Otherwise, you're just stuck. So that's the first and most important thing I did, which was to apply Taylor's theorem, essentially to recenter the polynomial. So, yeah. And then 2, if we have f of z is 4 times z minus 1 cubed, we can look at the rest of it as the perturbation. So the modulus of f of 2 is like 32 here, and the modulus of h2 of z is at most 24. Of course, 24 is less than 32, so Roche's theorem says there are 3 zeros inside the circle of radius 2, so 3 minus 1 is 2. There are 2 zeros in the annulus. So, yeah.
So because you care about the circle for r, because there was just strictly less than, like the specific boundary around the circle. I get how like we use the so I guess the modulus of z minus 1 equal to 2 or equal to 1/2, but would we be concerned about our zeros, like the zeros that we find being on the like that boundary, if that makes sense? Like being on the actual line, like,
But
you know what I mean?
I suppose we would, but when we establish the other inequality, it proves that's not possible. Like the one we did for the 1/2, like that inequality that we established for 1/2 shows you that there's no zeros on the, I think that shows there's no zero. Well, oh.
You know what I mean? Because then it's like you're assuming that a lot of your zeros are on the actual
Well, that's,
boundary, and then,
huh.
and then like when you subtract, when you're comparing like your function.
So you're concerned that, well, let's see here.
If you shifted z, it shouldn't really, like if you shifted it just a tiny bit, it shouldn't change the inequality.
Huh.
But I mean in terms of your like where your zero.
I don't know right offhand. I have to think about that.
Because then you don't know if you're not.
I suspect we've already proved it if we could just see it clearly, but you know, I'm not going to be dogmatic. There might be a gap here. You might be right. So.